So the next video is going to be about this problem for conservation of momentum that we have here. And basically this is kind of like the reverse of an inelastic collision. So you'll see what I mean in a second. So in this problem it says a sled of mass m3 is sliding on an icy frictionless horizontal surface with a velocity of magnitude v0. There are two riders on the sled, one with a mass of m1 and the second with a mass of m2. They both decide to jump off the sled. Their horizontal velocities are known and shown below. What is the velocity of the sled after they jump? Okay, so in order to do this, we are going to eventually be applying conservation of momentum. But before we do that even, something that's very helpful is to draw the before state and the after state. So the before state, you have this sled of m3, and then you have these riders on the sled with mass m1 and then mass m2. And this is going to be moving with this velocity v0. And then the after state, after, we're going to have this sled is going to move off in some direction. We don't really know exactly what direction it's going to go, but we'll say that it's going to go like this. So say that this has some velocity v3x and some velocity v3y, where we can say that v3 is going to be equal to the square root of v3x plus v3y, and these are both going to be squared. So here's our m3. Our m2 is going to be going up at this angle of theta 1 with some velocity v1. So this is going to be m1. And then our m2 is going to be going down with this velocity. This is going to be theta 2, and this is going to be v2. So our goal here is to set up a system of equations so that we can find what v3x and v3y are. Okay, so like I said, we're going to ultimately be applying conservation of momentum, and that's to say that the sum of the momenta before the collision, or before the occurrence of interest, is going to be equal to the sum of the momentum after. Okay, and both of these are vectors. So this says that sum px before is going to be equal to sum px after, and sum py before is going to be equal to sum py after. Okay, and so let's look at our px. So px, remember that momentum, which is a vector, is going to be equal to the mass times velocity. And breaking this just in the x direction, defining this to be the plus x direction, this to be the plus y direction, the initial momentum is going to be the sum of the masses. So this is m1 plus m2 plus m3 times v0 is going to be equal to the x portion of the momentum here, which is going to be v1 times cosine of theta 1 plus v2 times cosine of theta 2 plus v3x. Okay, now everything in this equation is actually known except for v3x, so that's kind of nice. But now let's look at what we have for our momentum in the y direction. So our momentum in the y direction, we don't have any momentum in the y direction initially, right? Because this is just moving in the x direction. So this is going to be 0 is going to be equal to momentum in the y after. So this is going to be, I'm missing some masses here. So this is going to be m1, this is going to be m2. Always check your units as you're going, and you'll notice I'll glance back at things and realize that I'm missing stuff. So then we have, this is going to be m3. So plus, okay. So then this is going to be equal to m1 v1 sine of theta 1 minus m2 v2 sine of theta 2 plus m3 times v3y. And so from these two equations, we can solve for what v3x and v3y are. And so this says that V3x is going to be M1 plus M2 plus M3 times V0 minus M1 V1 cosine of theta 1 minus M2 V2 cosine of theta 2 divided by M3. And V3y is going to be equal to, this one is going to be equal to M2 V2 sine of theta 2 minus M1 V1 sine of theta 1 divided by M3. And we could also say that if we want the magnitude of this, we can say that the magnitude of V3 is going to be equal to the square root of V3x squared plus V3y squared. And this is our entire solution parameterized in terms of what we know. Okay, so that's going to be it for this one. This one was a nice quick one. I'll see you guys in the next video.